Hello and welcome you all to the 14th lecture of this NPTEL course on electroweak interactions in the Standard Model of Particle Physics. And in the last lecture, we actually discussed how to construct a Lagrangian using fields, So, we gave this example of, constructing the Lagrangian with scalar field and also what we call the fermionic field or the Dirac field, and we constructed the Dirac Lagrangian. Now, today we are going to talk about a certain symmetry principles and how that symmetry actually leads to something like a conserved current and conserved charges is something very interesting, and that is what we are going to explore in today's lecture. Okay, so let us get started. So, first I would like to remind you that there are certain kind of transformations which we call global transformation, and there are certain kind of transformation which will be called local transformation. I will come to that distinction in a moment, but let us consider first that if you are invariant under certain kind of symmetry transformation, then actually that leads to certain class of conservation principles. So, that is basically the bottom line. Now, say for example, that if you have a time translational invariance, that means that if your system is kind of invariant under time translation symmetry like t going to t plus a, then one can show that this leads to energy conservations like dE dt is equal to 0. So, this is an interesting consequence that time translational symmetry leads to energy conservation. Similarly, if you have space translational invariance like your system is invariant under Ri going to Ri plus Bi, then you can show that this leads to a momentum conservation like dPi dt is equal to 0. On the other hand, if you are subject to rotational invariance like Ri going to some kind of rotation by a matrix Rij and Ri going to Rij Rj, then there is a conservation of angular momentum dji dt equal to 0. So, what I am going to do that I am actually going to illustrate this for a classical system using the Hamiltonian, which you are all familiar to, the standard construction of the classical Hamiltonian, where essentially I have H equal to P q dot minus L. L is the Lagrangian which we discussed in the last lecture, which is a function of q and q dot. Q is the generalized coordinates, q dot is the derivative of that, and P is what you call the canonical momenta that you can define, and the definition of P is essentially del L del Q dot. Now, let us consider the derivative of this Hamiltonian like dH dt. Now, if I do this exercise, what will happen? That first the derivative, the time derivative will act on this first term P q dot, that will lead you to P dot q dot plus P q double dot, correct? And then I can also have Lagrangian is a function of q and q dot. So, I cannot directly have the time derivative of the Lagrangian, but rather I have to do it in the chain derivative this thing. I will tell del L del Q into Q dot minus del L del Q dot into Q double dot, right. So, this is what I have. Now, I would also like to remind once again that P dot is essentially del L del Q. Now, how this comes? This comes from the fact that this identification that we already did, P equal to del L Q dot, right. So, now if you take the derivative like ddt of del L del Q dot, then you see that this becomes del L del Q, right. And so, that is how you have that P dot equal to del L del Q. So, therefore, I will replace del L del Q by P dot, and I will replace del L del Q dot by P, and so you see that P dot Q dot plus P Q double dot minus P dot Q dot minus P Q double dot, which is equal to 0. So, therefore, what you have is a H is essentially conserved Okay. So, there if you do not have an explicit time dependence in the Lagrangian or in the system, and that is essentially what it means, that you are invariant under time translation, then your Hamiltonian is conserved or any energy is conserved. Now, I would like to urge you that you also try to do the other examples like the conservation of linear or angular momentum, which results from the translational or rotational invariances. Let us come back to quantum physics. Now, in quantum physics, we all know that these observables are replaced by operators. Okay? So, the Heisenberg picture basically tells you the derivative of an operator d o dt is actually related to the commutator of that operator with the Hamiltonian of the system. So, this is the relation that d o dt is I commutator of h comma o. Now, I mean, I do not have to remind you, but still it is good to remember that the commutator of two operator is, what is that, like this is a b minus b a, right. So, this is what the commutator is. So, this is like h o minus o h. Now, if you see that if h o is equal to 0, then what does it indicate? It basically means d o dt has to be equal to 0. So, that basically means that the operator does not evolve or something. So, therefore, you can say that if dji dt is equal to 0, then that will basically tell you that ji and h, these operators actually should commute, or ji must commute with the Hamiltonian, and this is basically the statement of conservation of angular momentum, which requires the commutation with the Hamiltonian. So, this is classical then to quantum picture, and then we come to quantum field theory. Although we have not introduced the concept of what are the quantum fields so far, but we have described what are fields at least, and we will impose some quantization conditions on these fields so that they can have the particle like descriptions. So, the quantized fields in a sense will actually leads to the concept of particles, and that is the basic subject matter of the particle physics. But now, let us state one important theorem, which is essentially for a system which actually is consisted of some fields. So, let us consider that a system is described by the Lagrangian, which is actually this Lagrangian density, which are functions of the fields phi and their derivatives like del mu phi I, and the total Lagrangian is integral of d cube x L, this curly L, which describes the Lagrangian density. And we also know that the Euler-Lagrange's equation of motion in this particular case simply becomes del mu of del L del of del mu phi, right, del L of del mu phi minus del L del phi I is equal to 0, right. So, this is the Euler-Lagrange's equation for the system which has a Lagrangian density depending on the phi I fields and their derivatives. Okay. And now, we say that if such a kind of system has any continuous symmetry transformation, which leaves the action which is L integral of L dt invariant, that basically implies the existence of a conserved current. And what does it mean? What does it mean by having a conserved current? That is basically the statement that del mu of j mu x must be equal to 0. So, the conserved current that we are referring here is to essentially, so j mu is essentially the conserved current, and with there is also a conserved charge, and that conserved charge is defined by q integral of d cube x j 0 x, okay, which will also be a constant of motion. So, once again, to state the theorem of what we call this Noether's theorem. Amy Noether was a famous mathematician, and the theorem is actually refers to her name. And so it basically states that if you have a continuous global symmetry under which the action or the Lagrangian in general remains invariant, then this leads to a conserved current of the form, so that you can write something like del mu j mu x equal to 0. Now, what will be the exact form of j mu? That depends on the what kind of form of the Lagrangian that we are taking, and this also leaves constant or conserved charge, which will be simply q equal to integral of d cube x j 0 x. Now, let us illustrate this. I am not going to do a proof of Noether's theorem, but what I am going to do, that I am going to show you at least a couple of examples which actually shows you how you can find out the conserved current and conserved charges for some specific cases. And both these examples we have actually taken up in our previous discussions. The first example is to consider the Klein-Gordon fields, that is the scalar field basically phi x. And let us imagine that your Lagrangian is invariant under a transformation like phi x going to phi x plus epsilon del phi x. Okay? This is what I consider. Okay? So, we seek an invariance of the action under such a transformation. Like we demand, let us assume that the action remains invariant under phi x going to phi x plus epsilon delta phi x, right. So, what is the action? The action will be integral of L dt. Now, this L is integral of d cube x Lagrangian density, and this Lagrangian density, as we demanded, was actually, or rather is a function of phi and its derivative, right. So, this is what the Lagrangian density is a function of. So, this is, we seek an invariance of this action under the transformation that we just defined above. So, this is first statement. Now, let us see what happens. So, the del S, the infinitesimal change in the action will be basically therefore governed by integral of d4x delta L, right. Now, L is a function of phi and del mu phi. So, you can easily write this delta L, and that is del L del phi plus del L of del mu phi into delta of del mu phi, right. So, del L will basically have these two terms. Now, what I can do, that I can actually write these two terms, dress it up a little further. Kaise? I can also say that this delta mu, you know, the second term, the del of del mu phi, I use it interchangeably and I bring the del mu out and say that this is nothing but del mu of delta phi. Okay? Now, I am going to do a trick. I am going to write this term in first in terms of a total derivative. So, the first term remains as it is, del L del phi delta phi, that remains as it is. But the second term, what I am going to do, that I am going to write it like, first I write a term like del mu of del L of del mu phi into delta phi. So, therefore, what does it do? That this del mu in principle should act on both of these terms, right. However, what we have previously, we only have this term on board. So, therefore, in the process of adding the full derivative of the whole two terms requires me to subtract this term, and what this term would be? This will be the derivative acting on the first term, first piece of term, and that will be del L of del mu phi. ये टर्म मुझे हटाना पड़ेगा, तो ताकि मैं प्रीवियस जो टर्म है del mu of delta phi उसको रिटेन कर पाऊँ, right? So now let me arrange these terms a little and say I bring these two terms together with the delta phi sitting outside. What I have, that within the third bracket I have del L del phi minus del mu of which term? This will be this term which was here. So, this is actually del L of del mu phi delta phi, and then so this term is there, and I am actually putting this second term as a third term here, which is the integral of d4x del mu of del L of del mu phi delta phi equal to 0. Now, you remind me that if you have a Lagrangian which is actually a function of phi and del mu phi, for arbitrary delta phi we have this Euler-Lagrange's equation of motion, and what does it say? How it reads? The equation of motion will be del L del phi minus del mu of del L del of del mu phi, this whole thing is equal to 0, and this is nothing but Euler-Lagrange's equation of motion, correct? So, what does it say? That in this expression, in this previous expression that we actually have, if we adhere to the equation of motion, then this whole term actually goes to 0. And so, therefore, if you have to have delta s equal to 0, that basically means that this term del mu of del L del of del mu phi delta phi, that must be equal to 0. And you can now easily identify, we can write this full term as del mu of j mu equal to 0, and where this j mu is nothing but del L of del mu phi into delta phi, and this is precisely the conserved current that we were talking about. So, we see indeed that invariance of the system under a transformation which is like phi x going to phi x plus epsilon delta phi x. If you want to keep your action invariant under this transformation, this leads to a conserved current of this particular form, which has the generic form like del mu j mu equal to 0. Now, if you put it up in terms of components, then you can also say, okay, del 0 j 0 minus del I j I are also equal to 0, which comes from the del mu j mu term. And if I now take an integral of d cube x, so d cube x del 0 j 0 minus del I j I, that is equal to 0, or in a sense you can say that del 0 of integral of d cube x j 0, that is equal to integral of d cube x divergence of j. Now, the point is, here I am using the fact that del I j I is nothing but divergence of j. Now, you remember that divergence of a quantity of a vector integrated over volume can be related to the value of that function or field on the surface integrated over that surface, and this is what is called the Gauss's divergence theorem. Now, the point is, because this surface goes to infinity, if your system is valid up to that, and the current basically dies there. So, at x equal to infinity, so this integral of j dot s essentially goes to 0. So, this basically tells me that, okay, this conserved current implies further that del 0 q is equal to 0, or dq dt is equal to 0, where what is this q? This q is nothing but integral of d cube x j 0, and this is precisely what we call the conserved charge for the corresponding Lagrangian. Okay? So, this is what is called the conserved charge. So, this is an illustration of showing how the conservation, the symmetry transformation of the field, and the demand that you want your Lagrangian or the action in general invariant under such kind of symmetry transformation, this leads to a conserved current and a conserved charge. So, now I want you to do this exercise back home, that take the Euler-Lagrange's equation and assume that this Lagrangian is itself, and you can easily observe that there is a symmetry, which the phi can have, which I did not write explicitly here, but I will write it here, like this phi, when you take a transformation of phi going to something like a rotation e to the power I alpha phi, then you see that this Lagrangian actually remains invariant. So, there is a symmetry with which this Lagrangian is symmetric. So, this is a Klein-Gordon Lagrangian, this leads to the Klein-Gordon equation. So, if you take this symmetry transformation on the phi, the Lagrangian does not change, right. So, therefore, this Lagrangian is basically symmetric. Let me change this equation a little. Let me make this to be a complex scalar field which we take del mu phi star del mu phi, and here instead of m square phi square, let me put it like phi star phi, because if I take this transformation like phi going to e to the power I alpha phi, that basically means that phi must be a complex number, because otherwise I cannot rotate. So, it is like a rotation e to the power I alpha, you know that this is a kind of rotation in the complex plane. So, if I take this transformation of phi going to e to the power I alpha phi, then it is very easy to see that phi star will go to what? Phi star will go to e to the power minus I alpha phi star, and so therefore, phi star phi remains invariant, and so will be the del mu phi term. So, this is a symmetry of this Lagrangian. So, there is a inherent symmetry of this Lagrangian that we wrote. The question that I would like to ask you, that following the previous exercise that we just did, homework will be to find out the corresponding conserved current and conserved charge for this kind of a transformation. All right. Okay. I am going to do another exercise, and this is something very pertinent, because we are going to consider once again the Dirac Lagrangian. So, now you all remember that the Dirac Lagrangian, which gives rise to the Dirac equation, which we handled very well, and this Lagrangian was psi bar I gamma mu del mu psi minus m psi bar psi, where psi we know represents a spin half particle or a fermion. So, you can say that very well that this Lagrangian essentially describes the propagation of free electrons. Okay? Free electrons means it does not talk to anyone. So, it just moves with its wish. So, the equation of motion is essentially the Dirac equation, which is I gamma mu del mu minus m psi equal to 0, which we have already seen. Now, let us consider a global transformation, U1 global transformation, which is basically a rotation once again, and the rotation is governed by this parameter g alpha equal to e to the power I alpha. Now, alpha is just a parameter by which you are rotating, and you know U1 is basically a one dimensional group of unitary transformations, so that you have U dagger u or u dagger equal to 1, and this rotation, which is equivalent of alpha is equivalent to theta, is given by a single parameter, and this represents also what we call a Lie group. Okay. And in general, a Lie group element can be expressed in terms of g is equal to exponential of minus I T A alpha A, where T A are called the generators of the group, and you know for U1 case this generator is a trivial 1. So, that is why we do not have anything over there. The definition is T A is equal to I del G del alpha A for alpha equal to 0. These are called the generators of the group, and in general the generators also follow an algebra like T A T B is equal to I F A B C T C, where F A B C is kind of termed as the structure constant corresponding to that group. And for the abelian case, for the U1 one, the generators are trivial 1, as I said, and they commutes, and this falls into what you call an abelian gauge group. Okay. So, abelian group rather. So, we will come back to this once more, but for the time being what we want to see is to see that if I make a transformation, a rotation of the fermionic field by this e to the power I alpha, then what happens to the Lagrangian? That is the first question that we ask. So, suppose I am taking psi going to psi prime, which is e to the power I alpha psi, right? What happens to psi bar? You remember psi bar is defined as psi dagger gamma 0. So, psi bar is psi dagger gamma 0. So, following this definition, I want to find out, and psi prime is e to the power I alpha psi. So, what will be psi prime dagger? This will be essentially psi dagger e to the power minus I alpha. So, psi prime bar, that will be basically psi prime dagger into gamma 0. That is therefore, that psi prime dagger is psi dagger e to the power minus I alpha gamma 0, but e to the power minus I alpha is just a number. So, I do not worry of bringing the gamma 0 from that other side to here, and what I can say that this simply becomes psi bar e to the power minus I alpha. So, in the nutshell, what we said is basically that psi bar prime is essentially psi bar e to the power minus I alpha. So, if psi is going to e to the power I alpha psi, then psi bar prime will be psi bar into e to the power minus I alpha. Now, if you calculate psi bar prime psi prime, what will be that? Psi bar prime is essentially e to the power minus I alpha psi bar, and psi prime is e to the power I alpha psi. So, therefore, this remains the same. So, this e to the power minus I alpha and e to the power plus I alpha gets cancelled, and this is psi bar psi remains unchanged or invariant. On the other hand, what happens to the derivative term, the first term, psi bar I gamma mu del mu psi, that now becomes psi bar prime I gamma mu del mu psi prime. So, psi bar prime पहले लिख लेते हैं, this is actually e to the power minus alpha I alpha. Just because this is a number, I bring it on the left hand side, I do not worry about its position anymore. Psi bar I gamma mu del mu, and this term is e to the power I alpha psi, right, psi prime, and del mu, because alpha is just a number, and so del mu will not act on this. So, what happens that I will cancel eventually this e to the power minus I alpha and e to the power plus I alpha, and will eventually get what? I will get psi bar I gamma mu del mu psi. So, once again this term also remains invariant under the transformation that we actually talked about, which is psi going to e to the power I alpha psi. So, this also remains invariant. So, basically you can say that the whole Lagrangian, the Dirac Lagrangian, is invariant under a global U1 transformation represented by this rotation by e to the power I alpha. Now, the question that comes is that what will be the corresponding Noether current, the conserved current for this Lagrangian, which is invariant under U1 transformation, right. So, that is the question that we should ask. Now, remember that for this Lagrangian, for this Dirac Lagrangian, we actually find out one relation, because this gives you the Dirac equation, and from the Dirac equation we did show that there is a relation like divergence of j plus del rho del t is equal to 0. You remember, this is the continuity equation where we identified rho with the probability density, j with the probability current density, which nicely sums up to this equation del mu j mu is equal to 0, where this j mu is the 4 conserved current which has this entries like rho comma j. And what was the form of j mu? If you remember, this j mu was psi bar gamma mu psi. So, indeed this is a result of the symmetry that was inherent in the Lagrangian, which actually leads to this conserved current del mu j mu equal to 0. We did this whole exercise without knowing about it, but now we can visualize this as a consequence of having a global symmetry of the Dirac Lagrangian, like the U1 symmetry that we talked about. So, we have a conserved current indeed following Noether's theorem, and it is not very difficult for you to find out what is the corresponding conserved charge actually. All right. So, with this we stop now, and we are going to take up some more examples of symmetry arguments or symmetry principles in the next lecture. Okay. So, stay tuned, and we will have more on the symmetry arguments as we go on. Thank you so much.